For the past few years, I've been getting interested in low-level C development. For context, C is a very old programming language invented in the 70s, and despite being so damn old, is still one of the most compatible languages with virtually everything. It's really good at closely mirroring the computer's raw instructions, but at just a high enough level for humans to comfortably program in it. I've been having fun trying to use C to create more advanced programs with minimal dependencies, although usually I just import other code libraries that handle a lot of the more dirty and hard to develop parts of the software. However, a few months ago, I got the idea to try and code virtually everything from scratch, collecting all the code in single files that handle some fundamental part of software, such as, a file that handles graphics or a file that handles audio, etc. Everything within these files would be fully written from the ground up using no pre-existing code bases to perform its tasks, which is not only super fun and challenging to figure out, but also super useful since it has no dependencies. Anything that goes wrong can be instantly pinpointed and fully blamed on me, and anything about it can be fully internally reworked. All of these files would then be built up to create some software, the code of which would be virtually made entirely by my blood, sweat, and tears. Coding this would give me a solid understanding of the fundamentals of virtually all modern software and can help me understand why all of it is so horrible, not naming names. The whole goal of this is to create some software virtually entirely from scratch, only relying on two things: C, a very old and standardized programming language, and the operating system, a level low enough that most modern developers never work with it directly. I'll soon get into exactly what these offerings are and the context of these offerings compared to using more high-level forms of software creation, and to be clear, this is a horrible way of going about this. Most of the stuff you'll spend your time doing is just coding boilerplate to do certain things that other code bases do, but better, working with old, outdated, and unintelligible APIs, and you're going to see me struggle through all of this in its raw, unintelligible form. If you actually want to develop software, you'd much be better off just using the high-level, stable libraries to do whatever you need to do. This journey is purely just to see how they work, and for the challenge of having to do it without access to these libraries. So, I chose C for my software development because it's the most natively supported programming language for all of the busted APIs that I'm going to be working with. It's fairly simplistic, without many features to learn and care about, looking at C++, and its versioning is fairly standardized and basic, looking at C++. It's also fairly close to actual machine code, usually much, much closer than other languages, which gives it that low-level feel that we're going for in this series. And overall, I just like C, so this is what I went for. Suck it. The choice of C has limited me quite a bit, though. Most very high-level languages, like Java or C# have built-in support for a bunch of fancy stuff, like being able to create a window and draw things on it like shapes and text, and very few lines of code. These languages are able to do this because they're very new languages meant for modern, capable operating systems and applications. C, on the other hand, is our grandpa, meant for a wide array of things, such as development of the operating systems themselves. Again, this does mean that C is very compatible with a lot of things, but the C standard library itself, what C actually offers at face value, doesn't really provide much. Despite the fact that I'm using the C99 standard, created in 1999, the most C gives us is a few basic types, a bunch of math functions, a few functions for retrieving and modifying raw memory, basic input and output to a terminal, and that's just about it. Oh, and to add insult to injury, C has grown a few warts from being so old, so there's a bunch of little things that you have to resolve with how C interacts with certain compilers and contexts and such, especially if you're trying to get your code to work on other people's machines. So before I try getting past the barren wasteland that is C and into actually doing things, I've got to get comfortable in this wasteland. So in order to make C easier for me to use, the first thing that I'm going to create is a utility file, which I've aptly named muUtility. This file just makes a bunch of definitions and functions to make using C easier and to avoid all those pesky warts I was talking about. To make documenting it easier, I'm using a tool I made earlier called muDog, short for Documentation on Code Generator. I really tried to make that acronym work. It's just a basic C application that can scan a file and, using certain keywords, extract documentation written within the file itself and spit it out in a separate markdown file. So all those comments you see are largely just the documentation of the library that specifies whatever the hell's going on, and muDog extracts later. The entire utility file is wrapped in a macro designed to only declare itself once. It checks if muh is not defined, and if it isn't defined, it defines it, along with all the other utility stuff. This means that if this code is ever repeated, aka the user includes the file again or something, it avoids redeclaration, since it'll see that muh has already been defined and will not do anything. This idea will be expanded upon in other files I write, so remember this. The first thing that the file actually does after this macro mess is chop off the first wart that I need to account for. For context, I test compiling my files with two compilers, GCC and Clang, just to be more certain that my code will compile well on other compilers. And Clang kept throwing errors, calling certain functions provided by the C standard library unsafe and suggesting to use safer alternatives. I'm doing this on a Windows laptop, and Microsoft says that these safer versions just perform more checks to make sure that the data you pass in is good. But even if I wanted to use these functions, not all compilers and systems provide these, meaning that I'd rather have to, submit to the gods of Microsoft or build some complex macro system that calls the safer equivalents only if they're available, which I don't feel like doing. Thankfully, you can just define this special macro before including any files with these unsafe functions, and it basically tells Microsoft to go away. And this is the first thing that the utility file does. But this is not the last time Microsoft's shenanigans are going to get in the way of my coding. No, not by a long shot, not even in this episode. Just know that the first thing any file does from here on out is prevent Microsoft from whining, which is a horrible, horrible omen. Another thing I need to iron out are the few differences between C and C++. People often say that C++ is a superset of C, and while that's generally true, there are a few annoying exceptions. For example, I'm not sure if I'm just really stupid, but when I try to zero out a struct in C, which essentially just means setting all the values within a struct to 0, there's no standard built-in way I can do it in C that doesn't make C++ upset, and vice versa. For my experimenting, these two work separately in C and C++, but are not interchangeable in either language, meaning that I have to define a special macro for zeroing out a struct that automatically changes itself depending on if it's in C or C++. The syntax also seemingly changes in C++ if the struct is declared globally, so another macro needs to be made for that as well. I can't find anything online about this, and I could just use memset to set all the memory within any struct to 0, but Now, before I include anything from the C standard library, I'd like to share with you a cool way of doing it that I've figured out. Within the files that I'll be writing, instead of just including whatever file from the C standard library I need and then using its functions and such directly, I instead replace them with overridable macros. So, for example, instead of just including math.h and using the square root function, I instead use my own macro called muSquareRoot and assign it to just point to the square root function if it hasn't already been defined. This means that on default, the code checks if muSquareRoot hasn't been defined, and if it hasn't, defines it as just the normal square root function. Doing it like this, however, allows the user to define muSquareRoot beforehand as their own function, meaning that the file will see that muSquareRoot has already been defined and will just call whatever the user defined it as, therefore making it overridable. The advantage of this is that the user can implement their own equivalents and make the file use it, or possibly even implement trackers for when the file calls certain functions, which can make tracking memory usage a breeze since all manual memory allocation calls are automatically overridable. This is also expanded to all the types and virtually everything else that the standard library gives me, which is why you'll see stuff like uint32m instead of uint32t and muMalloc instead of just malloc. So in order to provide this whole system of overridable macros, a lot of this file is just creating overridable macros for various basic types that virtually every file I'm going to write will need at some point, such as the fixed width types, aka the signed and unsigned 8, 16, 32, and 64-bit integers. Whew, okay, now for the big boy that takes up the vast majority of the file, byte manipulation. Computers organize bits in packets of 8 bits, aka bytes, so when you have, say, a 32-bit number, it's internally stored and organized as 4 bytes. The ordering of these bytes can differ between computers, almost always being little endian or big endian. Since this is handled internally, the programmer usually doesn't need to worry about this, and little endian computers run code the same way as big endian computers conceptually. However, when trying to manually take a series of bytes and convert them into an integer equivalent, such as in trying to read a 32-bit value from a file, since files are just stored as a series of bytes, things get a little bit messy. We now have to worry about the exact order in which we're reading these bytes into an integer, with the process being slightly different depending on if the file is in big or little endian, how big the integer is, and whether or not it's signed or unsigned. So I created functions for each case, including 24-bit integers, since some files use that. Doing this includes a bunch of bit shifting that hurts my head, and I don't even really understand how it works. Ask Stack Overflow, I guess, but hey, I can read bytes into integers now, which is going to be super useful down the road. After this, I just sprinkled in a few quality of life features, such as a macro function for dereferencing a pointer that might be null, don't worry if you don't know what that means, as well as some macros for identifying which operating system is currently being compiled for, which will be useful very, very soon. But other than that, that's virtually everything I know and care about that needs to be cleaned up and organized for me to be able to use C comfortably from here on out. So, like I said, this is pretty much what standard C will be able to provide me, meaning that in order to get past basic terminal applications, I need to find a way to do more. In order to talk into the hardware onto my computer, I need to interface with the operating system, which lies on top of all of the hardware and manages all of it, giving me access to talk to it without giving me too much access to cause harm. After 2 seconds of Googling, you can figure out that Windows provides an API for doing anything you'd like on Windows that Holy Microsoft allows you to, and this API is called Win32. From what I can tell, with minor exceptions, virtually everything that you see software doing on Windows is somewhere under the hood using Win32 for everything. All the programmer has to do is link with the Win32 libraries, which come default with Windows, and I can code virtually anything that those Win32 libraries offer me. The issue here is with Win32, it sucks. It's really, really bad. It's basically a big soup of random functions that do random things masquerading as a cohesive API. The documentation really sucks and is super inspecific and horribly disorganized, so most of what I figured out was based on seeing how other people did it, looking up those functions in the Win32 API, and then using them to do whatever I need. Now, one of the key things that I want to establish before I start actually writing applications that are designed to do something is total operating system agnosticity. That means, in non-nerd language, that the code that handles the high-level stuff about the app never needs to care about what operating system is running. By separating all the operating system-specific code into its own little module, and then building the apps to use that, the central code of the app never needs to change depending on what operating system is running, and even better, doesn't need to change once new operating systems are implemented. I think it'd be fine to have a little bit of wiggle room, like stylizing the app in certain ways for certain operating systems to make it look better in that context, but these features will all be superfluous and would assumably have some default to fall back on for any operating system. So, I need to develop a library that handles all of that operating system specific code, and I decided to give it the codename muCOSA, with COSA standing for Cross Operating System API. That one's slightly less forced in my opinion. The idea is to describe an entire API for some operating system, but none in particular, and then implement it in each operating system that I want to support. For example, the muCOSA API would have some function, like muCOSA is keyboard key down, that returns whether or not a certain key on the keyboard is currently being pressed down. Then, internally, a Win32 equivalent function will be defined, probably called something like muCOSA W32 is keyboard key down, and the muCOSA function will call this Win32 function if Windows is currently running. So calling the muCOSA function triggers the Win32 equivalent to be called if Windows is running. However, this also allows other operating systems to be integrated fairly easily. I could code a Linux equivalent, muCOSA Linux is keyboard key down, and then have the muCOSA function called that if Linux is running. This whole system allows the top-level muCOSA function to be called whether or not the user is running Windows or Linux, and as long as both implementations are programmed well, they should run more or less the same, meaning that it is indeed cross-platform. There is one important limitation to this system. I only have a Windows laptop, meaning that I'm only going to be able to program good support for Windows. I could try and emulate Linux, but I'm afraid it won't run quite the same, and in turn will set my laptop on fire. I could dual boot Windows and Linux on my laptop, but I don't want to have to keep switching between the two and recording on both Windows and Linux. And either way, I think trying to code muCOSA the first time around to support both Windows and Linux might be a bit more than I can chew, so for now I'm just going to be sticking to Win32, and I'll probably come back and implement support for Linux when I feel like it. Another limitation to keep in mind is that I won't be planning to allow muCOSA to have support for things like mobile devices. muCOSA will be built to run pretty much exclusively on desktop operating systems, which in this case means devices with a keyboard, mouse, and a display where you interface with applications encapsulated in window boxes. This kind of just means everything that Windows, Linux, and macOS have in common. One more important thing to note before I dive into muCOSA is that things like Windows and macOS aren't called operating systems in muCOSA, they're called window systems. This is because Linux is a special child who can actually run in multiple different window systems, like X11 or Wayland, who handle all of the desktop OS stuff and whose specifications are quite different. This means that when it would come time to support Linux in muCOSA, I wouldn't support Linux, I would support X11 and Wayland, both of whom are different
Windows systems.
But this video won't make that distinction for now. Just know that when this video says operating system and when the code says Windows system, they mean the same thing for all the intents and purposes of this series. So, time to actually code muCOSA. Most big boy professional libraries split up their code into two sections, the header and the source, or the implementation. The header simply defines everything that you need to interface with the library without actually defining what everything does. For example, it'll say that a function exists, but won't specify the actual source code of the function. The source holds all of that actual code that makes up the actual functions, giving the whole library its proper functionality. This is useful for a bunch of situations, like when you want to be able to use a library in multiple different files, but don't want to have to duplicate the entire library several times. So in order to make my file more usable, it's split up into those two sections. The header is automatically defined if it hasn't been already, just like the utility file, but now the implementation will only be defined if the user defined a special implementation macro beforehand. This allows the user to include the file a bunch of times, with the only thing happening being the fact that the header gets defined once, allowing the library to be used. Then, when they want the actual source code to be defined, they signal it by defining muCOSA implementation before including it again, causing the source code to be defined. This is more good practice than anything else, and popular single-file libraries like the stib libraries use this method, but I'm not too concerned with it for now. I've only coded it like this in case anyone ever finds it useful, and I see all the other professional programmers use it, so, I've got to do it too. So, in the header, I get to define everything that muCOSA will do on the surface of things. This is essentially me programming the muCOSA API. One of the first issues I run into when trying to code a library this big is that I need to hold data over multiple function calls. For example, I want to have a function that returns how much time has passed since muCOSA began running, in seconds, which essentially exists as a program clock, and it's super duper useful in many circumstances that I'll get to down the road. But for this, I need to internally store what time muCOSA was initialized. The question then becomes this: where do I store this value and other values that I need to keep and modify over time? Where should muCOSA keep its stuff? I could store them globally, aka just declare a value in the file publicly so that all functions can just reference that variable, no questions asked, but what should I do if the user wants to run multiple instances of muCOSA? This situation may seem niche, and in all honesty it kinda is, but I still want the user to be able to do this if they ever need to, since hey, it's cool to be able to do that. So global variables are a no-go. Instead, I opted to encapsulate muCOSA into a context struct called muCOSA context, if you could guess, which will hold all of the data that muCOSA needs to do its stuff. Everything that's done in muCOSA is relative to a context, allowing muCOSA to operate fully encapsulated into a context, which allows the user to declare multiple contexts and have each one completely independent and unaware of another. Each context is tied to whatever operating system is currently running, meaning that this whole system has the added bonus of being able to run multiple operating systems at the same time if they're somehow existing simultaneously. This system does have the unfortunate side effect of the context needing to be specified whenever you want to do anything, meaning that the first parameter of any function in muCOSA is just the context. I do have a partial fix for this, but I'll get to it in a moment. For now, I want to talk about what's actually inside the muCOSA context struct. You may expect it to just be filled with a bunch of random stuff, but that's where you would be wrong. It only has 2 values stored inside of it. The first is an address to some memory in the computer, simply labeled inner. Basically, each operating system needs to store different stuff in order to do their things. The muCOSA context doesn't really care about what precisely that is, it just wants to encapsulate each different operating system's way of doing things and store a reference to that stuff when it's needed later. So internally, for Win32, I set up its own special Win32 context, which holds all of the storage for everything that the Win32 version of muCOSA needs to run. The memory for all of this is allocated at some point, which I'll get to in a moment, and the inner value in the muCOSA context is a pointer to that memory, a pointer to the operating system specific memory. In other words, the muCOSA context keeps a handle to the memory used to store all of the stuff that the current operating system needs. If Win32 needs something, it stores it in its own context struct, which is held onto by the muCOSA context. Whenever a muCOSA function is called in Win32 mode, and Win32 needs to access its context memory, it reads the value inner to get that memory, and uses it as it needs. This whole system allows muCOSA to hold onto the memory of whatever operating system is currently running, which I need in order to do a lot of things, which we'll see down the road. The second value stored within the muCOSA context is a result value. When the user attempts to do something in muCOSA, there's a chance that it will fail. Maybe the operating system just fails to do whatever was requested for some reason. Who knows? It just failed. So when the user calls a muCOSA function and expects it to do something, but internally whatever it was supposed to do failed, how do I inform the user that it failed? How should the user know something went wrong? How do I signal cases where something minute failed that will affect the way certain things work, but the function still overall did what it was meant to do? I decided to resolve all of this with the idea of a result value. Essentially, I defined a custom type, muCOSA result, which is just an integer. Then I define a bunch of unique values that correspond to certain things failing and how exactly they failed. For example, muCOSA Win32 failed create window is defined as some arbitrary unique value, and it indicates that in Win32, the call to create a window failed to execute. This means that the window which the user wanted to create was unable to be created. However, if whatever the user was trying to do fully succeeded, the value muCOSA success is returned, implying that everything went exactly as expected. All of these result values, besides success, are separated into 2 groups, fatal and non-fatal. Fatal means that whatever went wrong fully prevented muCOSA from doing what it needs to do. The previous value would be an example, since the window that the user requested for creation just flat out failed to be created, and there's pretty much nothing that can be done about that. When a fatal result is given, muCOSA cleans up whatever it was doing and continues on as if nothing ever happened. Non-fatal means that it partially failed, but not in a way that stopped muCOSA from doing what it needs to do. For example, if a particular thing about the window couldn't be properly set during its creation, but everything else went smoothly, a non-fatal result would be given, indicating that something went wrong, but not enough to warrant fully terminating the window creation. Almost all functions have result values, since almost all functions can go wrong besides destruction functions, aka functions that just destroy and deallocate something. Combine that with the fact that virtually every function also needs a context, and you end up with a system where the first 2 parameters of most muCOSA functions are just the context and a result value. This kinda sucks, as it leads to a lot of repetition, both on the API side and on the user side. There is a solution that I came up with though, and that is a global context. Essentially, muCOSA internally stores a handle to some context, which is labeled as the global context. Then, there are alternate versions of each function that use the global context to fill in one or both parameters, which internally are just defined as the normal versions, but using the global context as the parameter for the context. This is where muCOSA context internally stored result value comes in. If you know that you're just going to create one context and use it for the entire program's lifespan, you can set it as the global context, then just use the versions of the functions that fully assume the global context for everything, including the result value. This drastically simplifies things, since the functions don't take in a context, they just use the global context, and they don't take in a result value either, since they fill in the context result value instead. This means that for most people's usage, you can just use these versions of the functions, completely removing those first two parameters from any function that might have them. However, if you ever need to use multiple contexts or just want to store the result value somewhere else instead of inside the context, you can use the other versions of the functions. This does lead to a bit of bloat since we're redefining equivalents for each function, but it's actually really easy to define the alternate versions of each function as macros, meaning that the alternate versions aren't actually functions, but just a glossed up reference to the original function. This whole system is pretty damn complex internally, and I'm sorry for just smacking you right out the gate with all of this, but it's built to make using it externally fairly easy while still allowing everything to be super customizable. It allows the user to just use one context and assume it for virtually everything, or to split it up into multiple contexts and use them separately. Anywho, now that I've taken far too long to explain two values in a single struct, it's time to move a little bit beyond that. The first thing that I did once I defined the context and the result type is define a context creation and destruction function. Internally, the creation function figures out what operating systems are available, picks the best one, allocates whatever is needed for that operating system's context, calls whatever function that operating system has for initializing everything in its context, and optionally sets itself as the global context. For the destruction function, it simply figures out what operating system the context is on, calls the respective destruction function, and then deallocates all of the memory for it. Again, this system really just acts as a wrapper around an operating system specific implementation of this model. Like there's probably some Win32 creation and destruction function, and this whole system is built to just call those functions when needed. Once I had the context system figured out, it was now time to tackle the ultimate feat. Try to create and display a window, which I would first need to specify in the muCOSA API and then implement in Win32 under the hood. I decided to define the type muWindow as a pointer to whatever memory is needed for a window for the current operating system, much like how muCOSA context stores a pointer to whatever memory is needed for the context of the current operating system as a whole. Whenever you'd want to modify something about a window, the value for the window itself is just a pointer to memory that defines a window, which in the case of Win32 is the struct muCOSA W32 window. This struct will just hold everything that I'll need for a window in Win32 as I move on. Now that I know how a window will hold its own memory, I now need to have a function that creates and destroys a window, and this is where things get kind of complicated. Everything that makes up a window is actually pretty complex, and there's many things that can define it upon creation. So to just simplify all of this, I decided to encapsulate all of it into the struct muWindowInfo, which for now contains the name of the window, the width and height of the rendering space, or surface, and the x and y position of the surface relative to the top leftist pixel of the display space. All of this is then specified and passed into a window creation function, and the window will be created as specified per the struct. This description is fairly incomplete, and there's quite a few other things that can be made customizable upon creation, especially if we're allowing optional operating system specific information, but this version of muCOSA is meant to be fairly simplistic, so I decided against that. Again, these features can be sprinkled in later. Okay, so now that a window could theoretically be created, remember we're still working just in the API, this is yet to be implemented in Win32, how would I go about keeping the window up on screen? The easiest and probably best way would just be to set up a loop that keeps running as long as the window stays alive, and it's checked by this function, which simply returns whether or not the window is still active. Once the loop ends, you just destroy the window since the loop is closed, implying that the window is no longer active. This would occur once the user has pressed the X button on the window or something like that. For each loop, you simply call an update function on the window, which would process all of the events for the window. This loop is essentially each frame of the application, running and refreshing as many times as it can until the window is marked as inactive, to which everything is destroyed. Combine this with proper context creation, and you should theoretically have an application that just creates an empty and lifeless window until it's closed by the user, of course. But this is just the description of it, and now I need to actually implement each of these functions for Win32, which, The first thing I did was address arguably the biggest difference between muCOSA and Win32 right now, which is character encoding. Since everything that the computer stores is just numbers, they need a way to store and process strings of text. For this, each possible character is given a unique number. A character encoding is simply a standard that says these numbers are these characters. Unicode is currently the dominant character encoding, with virtually all text and virtually all modern software using Unicode to some extent, so Win32 naturally uses Unicode. And I've even decided that muCOSA should probably also use Unicode, so what's the issue? The issue is how you actually represent each number within the text data. Your gut instinct would just be to store each character, one after the other. However, Unicode has a lot of characters, with each character being given a 32-bit integer unique value, making each character a costly 32 bits to fully represent. This is really inefficient, as in certain languages, their characters fit in much smaller numbers that take up a lot less of those 32 bits. For example, most English text never uses a character that's not storable in 7 bits, since English characters comprise the first roughly 128 numbers of Unicode. So, different encodings exist for encoding multiple Unicode characters in sequence. These encodings use all sorts of bit data tricks to compress the size of each character, saving on size at the cost of processing speed. The speed generally isn't going to be a big deal for how I plan to develop my software though, so I use the most space-efficient encoding, UTF-8, whose methods are so clever that it can warrant its own video, but it's sort of irrelevant for this discussion. What is relevant in this video is Win32, who in classic fashion just kind of sucks for no good reason and uses the much beefier UTF-16. This means that if I want muCOSA and Win32 to be able to understand each other, I need to be able to translate both of these formats to and from each other. Thankfully, Win32 has built-in functions for this, so I just made a quick wrapper function for these conversions and went along my merry way. With this functionality in my back pocket, I could now get started on implementing the window creation function for Win32, which is a lot. First things first, every Win32 window needs to be created from a window class. This is the way it is because, according to Win32, it's useful to have a window class that each window is generated from, in case the windows that you're creating have certain stuff in common, which the window class can be used to pass attributes onto. For me and my purposes, it just kind of gets in the way, but I think it's arguable as to whether or not this is a good design choice. Also, big stupid mistake coming up. I misread the documentation and thought that each window must have its own unique window class, but this is wrong. You can just make one window class and create virtually infinite windows from it. That's like kind of the point of a window class. So in the code, you can see me register a unique window class for each window, which is really inefficient and hacky to have to implement since each window class also has to have a unique name. I didn't notice any of this until going back and writing the script for this, and I'll definitely be cleaning this up if I ever come back to muCOSA. Drape a big read the documents dummy over this and let's move on. One of the things I need to provide Win32 before I can register my window class is the H instance. And, you know, using Win32 excessively really makes it clear how many old features were attempted but just never fully materialized. It all just leads to a bunch of scattered, seemingly random things clashing together. So when an application starts in Win32, it is automatically assigned an H instance, which is like a unique tag for the application, except not really, more like just a unique tag for the actual executable file itself. A bunch of things in Win32 need this when registering or creating something, window classes included. You usually get it from the main function in Win32, but in the land of my lonely file that the user includes somewhere, we're far from being able to access anything regarding the main function. The best way to get around this is to access the globally defined image-base variable, which I don't even know or want to know what that is. All I know is that it holds the H instance, so you just access it from there. Thank you, Raymond Chen, for making this confusing and disorganized API navigable. So, with the H instance stored safely in the window struct, a unique window class name, and the Windows title converted from muCOSA's UTF-8 to Win32's UTF-16, I can fill out everything I need in the window class struct and register it. Are you having fun yet? If not, then have a gander at the window creation function, create window XW, with all of its beautiful parameters. If you're wondering, there are different versions of the window creation function for Win32, but I'm using the XW version. X here just implies that it's a more detailed version of its simpler equivalent create window W, giving me a few more parameters for further customization. The W implies wide character, aka UTF-16 text, which is needed since its alternative is A, which uses ANSI, which I'm far too afraid to even read its Wikipedia page on. The function that I am using takes in quite a bit of stuff, including styling, the window class that the window is tied to, the name of the window, its X and Y coordinates, its width and height, the H instance, yes again, as well as a few other values that I'm not using in my circumstance. And just like that, if everything went well, a window should be created by this point. Oh, and you also have to call another function manually to actually display the window, just sort of as like a final middle finger from Microsoft. A bunch of the stuff generated from this process is held onto within the window struct, such as the window class name, the H instance, the generated handle to the window, and the device context, which we'll get to much later. Remember this guy. We'll need these various handles for random stuff, particularly the window handle, since it's used in most functions regarding modifying or querying information about the window. Go figure. Thankfully, all of that was the hard part, and the rest of the functions needed in the basic window loop are fairly easy to implement. For destroying the window, I just release the device context, destroy the window, and then unregister its class, which is just a reverse order of how everything was created. For checking if the window is still active, the hilariously named function isWindow exists, which does as it implies, returns if the window is. It just returns if the window is still active or not. For updating the window, Win32 wants you to process all of the messages sent to the window since you last updated it. These messages are just everything that's happened to the window, such as the user interacting with it in certain ways, certain attributes about the window changing, etc. These messages are then sent to a custom user-defined function, sending you the information about everything that's happened so you can process these events and do things about them. But since I'm just trying to get a window to appear on screen, I don't particularly care about these messages for now, so I just pointed them to some default function back when I was registering the window class. I still need to process these messages to keep the window updated though, so that's essentially what the window update function is, just processing each message sent to the window. And specifically for this window, mind you, since you can also process all of the messages for every window you've created, but I decided to make it per window, and that's definitely something that won't cause any issues down the road that I couldn't have foreseen. None at all. So with all of these functions created and the proper muCOSA wrapper functions for them implemented, I should theoretically get a window popping up, and after fiddling around with some compiler errors, I got a window. I mean, resizing it is a bit funky, but other than that, it seems to be fully functional. Great, that took, what, 1,600 lines of code? Wow, this is gonna suck! Okay, we have a window, but it's just an empty, bland, and disgustingly uncustomizable window. The name of the game for the rest of this episode is just allowing the user to modify and query information about a window during the loop, allowing things to change every single frame. This includes all of the stuff that we've already defined in the muWindow info struct for creating the window, such as the title, dimensions, and position, but also a bunch of other stuff that I'll get to in a moment. Just you wait. For now, I need to decide how exactly the user goes about getting and setting these properties of the window. I could just create a lot of functions, like muCOSA window get dimensions, muCOSA window set dimensions, muCOSA window get position, and on and on and on, but I feel like that would lead to a lot of bloat and repetition. Instead, I had the lofty goal of wrapping virtually all window attributes into two functions, muCOSA window get and muCOSA window set. The functions take in whatever window we're talking about, whatever attribute we're talking about, and then whatever data we're talking about. The attribute in this instance is just some unique value tied to every defined window attribute, such as the dimensions or position. Then the data is simply just a pointer to memory for whatever attribute we're talking about. If we're getting information about the window, the function will fill the memory with whatever data is being requested. If we're setting information about the window, the function will read the memory and set the window's attributes to the data that it read. So, for example, if I wanted to get the window's dimensions, I would simply create an array of two uint32s with the first element to be the width and the second to be the height. I then call the window get function with whatever window I'm asking about, pass in the window dimensions attribute to tell the function that I'm talking about the dimensions, and then I pass it the memory for my dimensions array, to which the function will then fill in the array values as requested. If I were setting the window's dimensions, I'd simply fill in the values of the array for whatever I want the dimensions of the window to be, and then the window set function will read the values from the array and then set the window's dimensions to whatever values it read. Clean to use, requires very few functions. I do like it quite a bit, so I decided to go with it. I think it's a little bit confusing, but the syntax is just so clean I could not take the offer down. Internally, each of these functions are listed the laborious way in Win32. So, like the functions Win32 window get dimensions, Win32 window set dimensions, they're all declared, but I'm okay with it like this internally since I'd rather have each one be its own little function instead of just one massive function that handles all of the logic. The actual muCOSA function for getting and setting attributes simply has all of the functions on hand and calls the appropriate one based on the indicated window attribute, so it avoids bloat at the muCOSA level, which is primarily what I was aiming for. So with these attributes and functions defined, all I had to do was write those Win32 functions. Most of these are fairly simplistic and predictable. For example, setting the window title is as simple as just converting the UTF-8 muCOSA string to UTF-16, and then calling Win32's setWindowTextW function on it. But a lot of stuff is also not very easy to figure out, in particular the window's dimensions, and this is where things start to get a little bit weird. I decided that in muCOSA, a window's position and dimensions refer to its rendering space, which I called the surface earlier. It's essentially all the stuff that isn't the title bar, borders, etc. Just the primary thing that everything is drawn on. However, in Win32, the window is predictably the entire window. So when you get functions that modify the window's dimensions and position, it's actually relative to the entire window, not just the surface. After doing some digging in the documentation, I found out that the equivalent to the muCOSA window's surface, as I've defined it, is the window's client in Win32, and they essentially mean the same thing. So, for example, when retrieving the window's dimensions, I use the function getClientRect instead of the more commonly used getWindowRect. This idea seems good, right? Just use the client equivalents of the window functions. Except, no, some don't exist. For example, setWindowPosition, which is admittedly a bit of a misnomer, can set a window's position along with its dimensions and such. However, the function setClientPosition does not exist. As far as I'm aware, there's no default built-in way to adjust a Windows client dimensions. So my next best option is to grab the client dimensions that I wish to set, calculate its corresponding window dimensions using the styling of the window and the magical function adjustWindowRect, and then call setWindowPosition with the values that it spits out. Bill would be proud. A similar situation exists for getting the window's position. Yes, getClientRect exists, but from what I'm aware, it doesn't actually return the position of the client rect relative to the entire monitor space, which is what I want. Only getWindowRect does that, and it's only relative to the window, not the client. And adjustWindowRect won't help me here, since it only works with a window's dimensions. So, no matter what, I need some way to calculate the non-client area, which I'll label the frame extents, and use that to convert the window's position to the client's position. And you want to know something fun? There's no built-in way to calculate these frame extents either. There's like some default values that you can retrieve for the default window styling, but if you want to get the actual frame extents, regardless of what the window looks like, the best method I could find is to get the window's information, then the client's information, then use the magical function mapWindowPoints to map the client's information relative to the monitor space, and then calculate the differences between these coordinates. You don't need to understand that because I don't really either. All I know is that it works in most situations I've tested. I say most because I do know of some situations where it doesn't work properly, but I literally don't know how to solve it beyond that. You better be having fun by now. So with that function existing, I can now most of the time calculate the window's frame extents, which allows me to get the window's position, and from that use the frame extents to calculate what the client's position should be.
Intuitive.
And for setting the window's position, since setClientPosition didn't magically materialize into existence while I was coding the previous function, I just used the same approach. Around the same time that I was coding this, I also figured out why the window's resizing was being funky. It's because I didn't register a handle to the cursor when registering the window class. What does that mean, and why does that make that happen? I don't know. Nothing about the documentation for the function seems to mention this. Win32 is an API of survival, okay? And nature is not fair. This is just how it is. So to test if the window's position seems to be functioning properly, I set up a quick demo that just prints out the window's position every time you drag and drop it to a new position, and from what I could tell, it was working properly. I implemented the same thing for the window's dimensions, and it was looking good as well, so that's pretty much it for the basic attributes of the window, actually. There's definitely more that could be expanded upon, such as things like the window's focus state, minimized and maximized state, and on and on and on. But again, I intend to keep this version of muCOSA bare metal enough to get a basic piece of software running. But a window that simply prints if the user has changed some stuff about it is boring. How do I take in some actual input, like keyboard input, for example? Well, there's two sides of the coin to this, just like everything in muCOSA, which is how it's implemented in the muCOSA API, and then how it's thrown together in Win32 internally. And there's quite a few ways that you can go about taking input in an API. The most common is a callback function, which is just a function that the user sets, which will be called every time a keyboard key is pressed down or released. I do intend on implementing that in a bit, but for now, I just want to be able to check if a particular key is being held down or not at any moment, instead of responding to it as it happens. And there's a few ways of doing that as well. The most standard and common way is to simply have an isKeyboardDown function that simply returns if a given key is up or down, but I don't really like this approach since I don't like having to do all of the standard muCOSA function boilerplate every time you want to check if a key is down or not. I don't want you to have to call the function each time you want to know if a key is down or not. So instead, I came up with a key map system. I'm sure this has been implemented in other APIs, but because of my limited experience in the field, so to speak, I haven't seen this system before. Essentially, instead of querying for individual keys being up or down, you instead grab a key map, which is essentially a list of booleans, with certain indexes into the list corresponding to the state of certain keys. So, for example, if you ever plan on taking in keyboard input, you grab the keyboard key map. Once you have that, it's trivial to check if certain keys are down or not. For example, if you want to know if the key A is down, you index into it with the value muKeyboardA, and the value of this boolean indicates whether or not the A key is down. Better yet, since everything about a window is manually allocated, once you grab a key map from the window, that key map is valid as long as the window is alive, with its values theoretically automatically refreshing every time the window is updated, with you not having to grab a new key map every single frame. The values are always there and you can always check them. This is about as low overhead as I think you can get for checking the state of a key at any given time, and in my opinion, it's really clean and flexible, so I just decided to go with it. Internally, I can even make the key map itself a window attribute that can be retrieved, meaning that you can just call a window get for it once at the beginning of your program, and always be one index into an array from knowing whether or not a key is down. It's a pretty nice system in my opinion. The first challenge to getting this working is actually defining the value for each key. I only defined keys that are supported on Win32, whose defined key set is strange? Win32 uses virtual keys, which have a set of defined values that include keys like PA1, heir of, and OEM102, but it's missing keys like semicolon or backslash. I presume there's some magical way to detect keyboard input for these keys, or maybe I'm just using the wrong system. I mean, all of these values are in the legacy features category, but just Googling Win32 keyboard input links you to a modern page that lists these values as the primary way of getting keyboard input, so who knows? If it works at this point. I won't be using the keys that Win32 is missing for now, so I'm not too bummed about the whole thing, but I'm almost definitely going to go back and figure out how to map those missing keys later at some point. With all of this defined on the muCOSA side, it's time to actually go into Win32 and implement all of this. The way Win32 sends keyboard input is via messages to the window, which, if you'll recall, you're able to intercept by pointing Win32 to your own function, which will be called for every single message with some information about what happened. This seems all fine and good until I ran into an unexpected situation. The function that gets called by Win32 for each message, which is called the proc function, short for procedure, only passes the Win32 window handle and then information about the message. And if I want to update the muCOSA Windows key map upon keyboard input messages, I need an actual handle to the muCOSA window, not the Win32 window. So the question becomes this. When given just the Win32 window handle in the proc function, how do I find its corresponding muCOSA window handle? And this is where the fun begins, my friend. You see, I'm kind of constrained here. I don't have access to the muCOSA context either, since all I have is just the Win32 window handle, so no matter what, I have to use some global variable to figure all this out. My initial idea was a globally stored lookup table that holds every single Win32 window handle and its corresponding muCOSA window. Every time a window is created, it's added to the lookup table, and every time a window is destroyed, it is removed. Then, in the proc function, it scans through each Win32 window handle in the lookup table until it finds a match, and is therefore able to get the corresponding muCOSA window handle. This would suck to implement in C, as C's low-level memory management nature makes arrays that increase and decrease in size with unique objects very difficult to program efficiently. But, if you can believe it, it gets even worse. I've been neglecting to mention multi-threading for a while, and it's been a huge reason for why I've been avoiding global variables and keeping everything so local. This is because multi-threading allows multiple threads of code to run simultaneously, and the last thing you want in an environment like that is shared state, where two different threads are reading and writing to the same resources at the same time, the behavior of which is completely undefined when it happens. You usually fix this by adding some locking mechanism to make sure that the same resource isn't accessed by two threads at once, but I didn't want to build this internally, both because it'd be an absolute headache and that it's fairly easy for the user to implement it themselves on just the resources that they know might be accessed by multiple threads. The rule of thumb with the code that I've written so far is this: if the same object is being accessed by two threads at once, things are probably gonna go bad. This largely means objects within a context, like a window. I allow minor exceptions to this in particularly rare circumstances, and document the exceptions that I know of, but having a global array that can be accessed and changed anytime a window is created, destroyed, or updated across all muCOSA contexts is just begging for unpredictable behavior. The fix to make our array actually thread safe is a lock, to which I've decided to use a
spin lock.
Put simply, the array has a big lock over it. If it's
unlocked,
a thread can lock it and take ownership of it, doing everything it needs to do, such as reading or writing data to the array. During this time, if another thread tries to come in and do something, it'll see that it's locked and will wait. This can even support a queue of threads waiting for the array to be unlocked. Once the owning thread is done with whatever it needs to do, it'll unlock the thread, and in first come, first served style, a waiting thread gains ownership and locks it, doing the work it needs to do before letting any other threads take control. It's sort of like a waiting list for every single thread that wants to use the array. It prevents two from doing the same thing at the same time. All of this happens globally, in some corner of the Win32 API, serving all traffic for windows being created, destroyed, and scanned for in proc functions. This whole system wasn't too challenging to implement, it's just a little bit stupidly convoluted is all. Upon any Windows creation, it locks the array and adds itself to the array, and upon any Windows destruction, it locks it up and gets rid of its entry. Whenever the proc function needs to find a muCOSA window based on a Win32 window, it locks the array and then just scans through each item until it finds a match. It's annoying that this has to be done, but I think it works okay enough for virtually all intents and purposes. It's definitely not the most memory efficient approach, especially in regards to how it handles windows being destroyed, but I can't imagine it being an issue in any real circumstance. But then again, I did, make muCOSA support multiple operating systems running at once, so who do I think I am? Anywho, with this system in place, and after some minor bug fixing, I can now figure out the muCOSA window in our message handling function, which means that I can actually finally start processing messages for keyboard input. Win32 gives the program key input in the form of two messages, WM key down and WM key up. This message gives me the virtual key codes that I was talking about earlier, which I can just convert to a muCOSA key using a big switch statement, returning an unknown value to indicate that the key received has no muCOSA equivalent, to which I just disregard it. There is a slight Win32 hiccup, as it's never that straightforward. The way Win32 gives some keys, they need to actually manually be split up into their left and right equivalents, which is done with some strange Win32 sorcery that Stack Overflow definitely didn't help me figure out. But other than that, once I've mapped the virtual key code to a valid muCOSA key, I simply change the state of whatever key it is in the key map array. This whole system basically just listens for Win32 messages saying when a key changes, and changes the corresponding element in the key map array to indicate as such. And after all of this, I get to hold down the W key on my keyboard, and the terminal prints W in response. So worth it. My next idea was to modify the demo to allow the window to move around using the WASD keys, proving both that key input and setting the window's position works. Unfortunately, in order to do that, I actually need to implement muCOSA time, which I talked about earlier if you remember, like all the way back then. The reason why I need the time for this is because frames take an unpredictable amount of time to process. Currently, because I'm doing like nothing each frame besides basic window updating, quite a few frames are being processed every second, which makes the speed of each frame very fast and wildly fluctuating. This means that if my frame-by-frame logic was if key W is down, move window 1 pixel, the window would probably shoot upwards since the frames are being processed so quickly that 1 pixel per frame is often hundreds and often near thousands of pixels per second. The logic is being performed too many times too quickly because each frame is just being processed so quickly. There are several ways to fix this, including methods like delta time multiplication, which I'll get to down the road, but for now, just to keep things nice, simple, easy, and predictable, I'm going to use frame timing. Let's say I want to process a fixed amount of only 60 frames per second, which means that anything I do per frame is done 60 times a second, with each frame lasting roughly 1/60th of a second long. This makes timing really simple since I can do the frame-by-frame calculations knowing that it's going to be done roughly 60 times a second. To achieve this, I need two things. First, I need to know how long the current frame has been going on for, and second, I need to be able to sleep for the amount of time necessary to achieve 60 frames per second. The logic goes like this. At the end of a frame, I calculate how long this frame has been taking to process by keeping track of what time the frame started and what time it is by the end of it. If that amount of time is under 1/60th of a second, the frame was processed quicker than a rate of 60 frames per second, and I can simply sleep for the amount of time necessary to make the frame time roughly 1/60th of a second. This essentially acts as a pause timer, deliberately taking breaks to ensure that each second contains roughly 60 frames. And to be clear, everything here is based off estimations. It's virtually impossible to get an exact 60 frame per second rate for so many reasons, such as timer inaccuracies, extra unaccounted time spent doing all the time calculations, and on and on and on, but it's definitely accurate enough for my purposes. So this whole process of frame timing requires only two functions that I need to integrate into muCOSA. A function to get the amount of time it's been since the muCOSA context was created, in seconds, with a fair amount of decimal accuracy, and a function that pauses code execution for a given amount of seconds, again with a fair amount of decimal accuracy. And just for more flexibility, I decided to throw in two more functions. The first one actually sets the amount of time a muCOSA context thinks it's been since it's been created. And the second function gets the time, but without the set time function modifying it, always truly representing the time. But these functions aren't going to be used anytime soon, so you don't need to worry about these. Implementing this for Win32 was actually pretty easy. The way you get the current system time in Win32 is weird, and I'm not going to pretend to understand it, but it does work. So, when a context is created, I log exactly what time it was created based on the current system time. And then, whenever the time needs to be retrieved, I just get the current time and subtract the creation time from that, returning how many seconds it's been since the muCOSA context was created. The overwritable time and non-overwritable or fixed time are stored in two separate variables for this purpose, in case you're wondering. And for sleeping in Win32, the function sleep exists, which can sleep for a certain amount of time with accuracy down to the milliseconds, which is fine by me. And so, with those implemented and the wrapper functions encapsulating them, I could set up my frame timing system and move the window at stable and fixed speeds using my keyboard, retrieving and modifying the window's position a few pixels each frame if certain keys are being pressed down. And just like that, smooth movement. Awesome! And with a handful of extra code, I was able to test the dimensions of the window too, modifying the dimensions based on the arrow keys, which thankfully proves that everything works as far as I'm aware. So, now that I have keyboard input, I wanted to get mouse input working. This entails two different types of input, the mouse button input, like if you're holding down left click, and where the cursor is on the screen relative to the window's surface. I decided to implement the mouse button input as a key map, internally working very similarly to the keyboard key map, but now by intercepting the various, mouse button down Win32 messages and modifying the mouse key map based on that. For the cursor position, I decided to make it a window attribute that can be retrieved. Thankfully, this process was quite easy. The function getCursorPosition exists, which retrieves the cursor position relative to the entire monitor space. So I could just use that, retrieve the window position using the function I wrote for it earlier, and then return the cursor position relative to it. To test if I had all of this mouse input working, I decided to add dragging the window around using the mouse to the demo. Essentially, if the user was holding down the mouse button anywhere on the window surface and moved the cursor, it would calculate how much the cursor had moved and moved the window along with it. This should result in a window that can be dragged by its surface, similarly to how you can, also drag a window by its title bar. And after some interesting results, and then some even more interesting results, seriously, what is happening here? I was able to get it working. At this point, I'm just getting certain miscellaneous functions off my checklist. For example, the cursor style. On desktop operating systems, there's several different ways that your cursor can look in various different contexts. Being able to change the cursor style in response to certain things happening in the application is really useful for making your software seem more integrated into the operating system, so I wanted to implement it. Most desktop operating systems have a basic set of cursor styles in common, so I loves cross-platform cursor style options and used that. For the muCOSA API, I just made each window have a cursor style associated with it that the cursor becomes whenever it's within the window surface. This makes integrating the cursor style into the muCOSA API really simple, because you can just make the cursor style a window attribute that can be get and set, allowing the user to set the current cursor style per window. When it came to actually implementing this in Win32 though, I had a bit of a hard time with the documentation. I had trouble finding the default cursor styles and somehow ended up on this Polish Chomik cloud site, but I eventually found where I should be. If you'll remember from like half an hour ago or something, I had to get a handle to the cursor when registering the window class, so I thought that maybe I need to use that and set its cursor style or something, but I couldn't find any function that does that. I found the function setCursor, but it doesn't take a window or anything, just a cursor handle, and the description just reads sets the cursor shape. So I just call that, locating what cursor style I want with the function loadCursor, and it looks like it works, but anytime I move the cursor, whatever style I set it to just disappears. After doing more digging, I found out that Win32 actually changes the cursor a bunch, sending messages to indicate such, under the message tag wmSetCursor, and so Win32 was just overriding my call to set cursor. I decided to fix this by just responding to each wmSetCursor message by setting it to my cursor style instead, and it worked. It actually worked a little too well, though. You can see me hovering over where you would usually resize the window, but it doesn't change style to the resize cursor like it usually would, just staying stuck to whatever cursor style I set it to, because we're completely overriding the cursor style. I tried fixing this by only overriding it when Win32 attempts to make the cursor the default style, so that would allow Win32 to set it to the resize cursor when on the edges of the window, but I just couldn't get it working. So, despite my many attempts, I decided to just kind of hack it and only set the cursor style when the cursor's position is within the window surface via just manually checking the cursor's position. It's stupid, but it does indeed work, so I just decided to go with this. I assume there's some better way to do this that I'm missing, but hey, if it works, it works. So now that I've created some general basic window functionality, and looking at how long it's taken me to get here even in video form, I think I'll end it for this video. This entire setup has just been to lay a solid foundation for how exactly the creation and management of a window could be done in a cross-platform manner, and I think I've fairly achieved that more or less. Win32 is definitely a pain to navigate and use, but it was by no means like impossible, and I mean, if I'm going to code software from scratch, I've got to interface with it at some point, so I'm glad that I'm quarantining it into just muCOSA. The next video is going to be about getting graphics to render, since all I've got up to this point is just an empty, boring window. Getting things to that point will actually entail a lot more operating system specific code, as you'll see in the future, but after that, I can promise you that we won't be dealing with Win32 much, or at least not for a very long time. And trust me, it'll be much, much harder than you'd expect, but you could also say that about this video, I guess. Anywho, that's all I have to say for now. Bye.